Welcome to this lecture series in linear algebra. We will continue our discussion with inner products, and in this lecture we will establish many of the properties that we see in Euclidean spaces that are provable in the context of abstract vector spaces equipped with an inner product. So let us quickly recall what is an inner product space. So an inner product on a vector space. So let's say we are talking about real vector spaces. I will mention what we said about complex vector spaces. So if V is a real vector space, then an inner product on V is a map of this sort, which enjoys these properties. The first four just mean that this is a bilinear map. This is called positivity property, which says that if you take the inner product of two vectors, you always get something non-negative, and the only way to get zero is when you use 0 in both slots. Okay. So, you use 0 in place of V. If any of the slots have 0 in it, then of course the inner product will be 0. That follows immediately from bilinearity. Okay. And lastly, we have symmetry property, which is that you take the inner product of U with V or the inner product of V with U, you get the same thing. So that is what happens for real vector spaces. If V were a complex vector space, then the definition changes a little bit. Only the star-marked statements, they change. And in that case, we would have to put a complex conjugate here, and here also a complex conjugate. So I could have just defined it for any vector space and put complex conjugates here, because that would cover the definition for a real vector space also, because the complex conjugate of a real number is the same real number and it doesn't change anything. But anyway, so we have recalled the definition of an inner product, and the point of an inner product is to capture the geometric properties that we see in Euclidean spaces. So one should think of an inner product as an abstract or abstractification of the usual dot product that we are familiar with. So we now can think of the notion of distances and angles in a vector space. Particularly, the norm of a vector is defined in this fashion, and this should be thought of as the distance of the vector from the origin. Okay, because what is this quantity? You can think of this as the dot product of the vector with itself, and hence it should be the square of the magnitude of this vector, and this is precisely, just formalizing that. Okay, so all we are trying to do is just induce some geometry in an abstract vector space. And the notion of inner product makes sense only when we are dealing with real or complex vector spaces. All right. Here are two problems for practice. And now let us get started. So first we will prove a lemma. So here we are working with an inner product space, so it is irrelevant if it is real or complex. All these statements are true either whenever we don't say otherwise, all these statements are true either for real or for complex vector spaces. They are true for both. So if we are working with a real vector space, there is no need to write this, but writing this does not harm us. So this one single statement is applicable to both real and complex vector spaces. So what is the statement? The statement is that whenever you pick two vectors in an inner product space V, then the norm squared of the sum of these vectors is this quantity. So let's just quickly prove it. So norm squared by definition is, I want it to be aligned. So by definition, this is the inner product of x plus y with x plus y, which is, you just expand out. So let us use the additivity property that is enjoyed by the first slot. I'm doing it very, very slowly. Okay, and now let us use the additivity property enjoyed by the second slot. This is norm x squared, this is norm y squared, and so let's write that. This is the complex conjugate of that guy. true both in a real vector space or a complex vector space. And a complex number plus its complex conjugate is twice of the real part of that complex number. So we get what we had written. Okay, very simple result. But this has an interesting consequence. This is called the parallelogram equality. So fix two vectors x and y in an inner product space V. Then we have this equality. And the proof is very simple. First, we have this. Immediately from the previous proposition. I mean, this was the previous proposition. And now apply the previous proposition to this guy. So just think of x minus y as x plus minus y, and apply the previous proposition to get norm of minus y square, but norm of minus y square is same as norm of y square. Okay, so this is plus real part of x dot minus y. So I will always say x dot minus y to just mean the inner product of x and minus y, yeah? So I tend to use this phraseology, which is probably not the standard thing. Anyway, so now we just use the fact that this comes out with the complex conjugate, but this is already a real number, so this just comes out with a minus sign. And that's it. Now you add. If you add these two equations, you get precisely this. So this is called the parallelogram equality. And the geometric meaning is very clear. So we have two vectors, x and y. So let us complete this parallelogram. Yeah. So this is x plus y. And this, so this orange thing is x plus y. And this is x minus y. Maybe I'll use a different color. This is x minus y. So when I say this is x minus y, I mean, if you translate it and have this point would be x minus y. But what would be the length of this guy? The length of this guy would be norm of x minus y squared. I mean, the length of this guy would be norm of x minus y. So the proposition is just saying that you take the sum of the squares of the length of the diagonals, or you take the sum of the squares of the sides. It's the same thing. And this is a purely two-dimensional fact, so you can prove it using Euclidean geometry also, just high school Euclidean geometry. Okay? So that's the geometric meaning of the proposition. It's saying something about a parallelogram, and hence it is called the parallelogram equality. Okay. Now for the Pythagoras theorem, or Pythagorean theorem. So again, we have an inner product space, doesn't matter if it is real or complex. Fix two vectors in it, x and y. Then we say x and y are orthogonal if x dot y is 0. And note that here the order is irrelevant, because if this is 0, then this is also 0. Maybe write that again. This is also 0 simply because what is this? This is the complex conjugate of that guy. So here the order is irrelevant. What I'm trying to say is, if x is orthogonal to y, then y is orthogonal to x. Okay, so that's the definition of orthogonality. The geometric meaning is, suppose we have, this is x, then you can think of it as follows. If suppose y is of this sort, where this angle is 90 degrees. Of course, in an abstract vector space, this is not a very true picture, but this is how you should think about it. When we say x and y are orthogonal, you can picture it this way. That they are at quote-unquote 90 degrees to one another. Okay? So then obviously we have a Pythagoras theorem. If x and y are two vectors which are orthogonal to each other, then the square of the hypotenuse of the triangle formed by x and y. So maybe I'll import this picture. So imagine a triangle where one side is denoted by the vector x, the other side is denoted by the vector y. And what is this side? This side is x plus y. And if x and y are orthogonal, then this is 90 degree. And what this is saying is that the sum of squares of the sides is the square of the hypotenuse. So we need to prove it, even though we know Pythagoras theorem from high school geometry, we need to prove this thing. And the proof is that same lemma that we used to prove the parallelogram equality. So x plus y squared is that thing, but these x and y are orthogonal, so this guy is 0, and hence what remains is only this part. That's all. That's the proof. So it is actually a trivial theorem in the context of inner products. When you're proving it in high school geometry, it takes quite a bit of creativity to prove it. And it's not like this gives you a simpler proof of the Pythagoras theorem. That's not what is happening here. The Euclidean plane has its own axiomatization, and within that axiomatization, this kind of proof will take. If you really want to just use this proof, it will take a lot of work. You cannot avoid it. Anyway, you can ignore that comment. Now let's go to the next section. So this is the orthogonal decomposition. Before I state the formal theorem, here is what we want to do. We have a vector v, assume it is non-zero, and we have some vector u. Okay? What we want to do is break this vector or write it as a sum of two things, one thing along v and one thing perpendicular to v. That's what we want to do. So just imagine the span of these two vectors. That will be a two-dimensional thing, assuming both are non-zero and they are not linearly dependent. So then it will be a two-dimensional thing. And basically, you can think of that thing as R2 if we are working with a real vector space, even though what we are going to say is also true for complex vector spaces. So in that two-dimensional vector space, we are just saying, okay, project it or drop the perpendicular from this point to that point, and drop the perpendicular from this to the line perpendicular to it. Basically, this is, in physics, we call this a resolution of a vector in one direction and the orthogonal direction. So that's all that what we are going to say is all about, geometrically speaking. Okay, so what we are saying is we be an inner product space, regardless of whether it is complex or real, and fix a non-zero vector in the vector space. And for any vector x, we can write it as a sum of two vectors, y and y prime, where y is along v, meaning it is in the span of v, and y prime is perpendicular to v. Okay, we can write it this way, and there is a uniqueness to it. So we can write this uniquely in this way, which I haven't included in the statement. So we can write uniquely right. So there is only one way to write x as a sum of two things which have these two properties. Okay, so let's prove it. So first we will do uniqueness, and the proof of existence will be informed by this proof of uniqueness. So say x is alpha v plus v prime, where alpha is some scalar. So this f could be real or complex depending on whether v is real or complex, and v prime is orthogonal to v. So perhaps I should have discussed this notation. When we write this, we just mean that v prime is orthogonal to v. Here, so when x and y are orthogonal, one may write this. That's the notation. Okay. So yeah, so suppose x is written in this fashion where alpha is some scalar and v prime is orthogonal to v, then just dot both sides by v. And what is this guy? This guy is 0 simply because v prime is orthogonal to v. So that guy is 0, and hence what we get is which implies, or I'll write norm v square because that's what it is. This is equal to alpha. Okay. So there is only one alpha. If at all you can decompose x in this fashion, there is only one alpha that can do it, which is this, which we can just explicitly write down. And since there is only one alpha that can do it, there is only one v prime that can do it because you just shift it to the left side. So you can also explicitly write this down if at all there is there exists such alpha and v prime. So that finishes the proof of uniqueness, and the proof of existence just comes out of it. So for existence, we will just explicitly write down this decomposition. So just see that x equals x dot v plus x minus. Just note that this is a desired decomposition. So clearly this is in the span of v, and this is orthogonal to v simply because when you dot it, you will get 0. Because the first part will be x dot v, and the second part will be you already have an x dot v, but this v dot v will cancel with the denominator. So this is a desired decomposition. And the geometric meaning is clear. This is basically that component, this part. This is the length of the projection. Just think of it in terms of high school physics. And this is the vertical part. Okay? So this is just mimicking the proof of the resolution of a vector along two perpendicular lines. Okay? So now we come to the next part. The Cauchy-Schwarz inequality, an extremely important thing. So fix an inner product space V. Again, it could be either real or complex. Then for any two vectors u and v in the vector space, we have this inequality. So the modulus of u dot v, if v were a real vector space, this is just the absolute value of this real number. But if v is a complex vector space, this is the modulus, the magnitude of the complex number, is less than the product of the norms of u and v. So again, geometrically, this is saying something very meaningful. You take two vectors, u and v, then the product of the lengths of these two vectors dominates the, this thing which is supposed to mean the length of this times the length of this times the cos of this angle, and hence the domination should be at least heuristically clear, because that is what it is trying to say. However, we need to prove it formally. So that's the first part of the statement, this inequality. The second part of the statement is that equality holds if and only if u is a scalar multiple of v or v is a scalar multiple of u. Okay, so basically when they are linearly dependent is when equality holds. Okay, so let's prove this. So we will use the decomposition that we saw in the previous section. So we will do the proof when v is non-zero, because if v were 0, this is trivial, right? This trivially holds. So suppose v is non-zero, then the vector u is, as we saw in the previous section, let me just see if I made a mistake. No, this is fine. Yeah. So now by Pythagoras theorem, why can we apply Pythagoras? Because these two are orthogonal. We saw this. This is what we saw in the previous section. So by Pythagoras, we see that norm of u square is the square of the norm of that, which I'm going to write. That's the square of the norm of this thing. Why is that? Because the square of the norm of alpha v is by definition alpha v dot alpha v. This first alpha comes out as it is. The second alpha comes out with a complex conjugate. And you get that. Now alpha bar is mod alpha square and v dot v is norm v square. So that is what is going on. Okay. So here I should have written a power 4, which I missed. All right. So that's the square of the first part, and the second part gives us something non-negative. Right, just something non-negative, which implies so what we did is, since this is non-negative, we get an inequality here, and we have cancelled this 2 with the 2 here, so we get that thing. And now if we rearrange, we get the correct, we get the desired inequality. Right. Okay, so that establishes this part. For the second implication, equality holds if and only if equality is maintained when we come from here to there, and that is maintained if and only if this is 0, not just non-negative but exactly 0, which happens only when this is 0, which means u is a scalar multiple of v. So when v is non-zero, it follows that equality holds when u is a scalar multiple of v. And when u is non-zero, you can say the corresponding statement, and therefore this holds. Okay, and geometrically, we see that equality holds only when these two vectors are aligned, which as it should. Okay, so that's the Cauchy-Schwarz inequality. And lastly, the triangle inequality. So again, let me state geometrically what it is trying to say. It is saying a very simple fact that suppose we have a vector x, a vector y, and we have the sum of those two vectors, then the norm of this plus the norm of this dominates the norm of that. So maybe I should write uv and u plus v because that's how I have stated it in the theorem. That's all the triangle inequality is saying. All right. And there is a clause which asks for or tells us when and exactly when the equality holds. That part I will leave as an exercise, but let me prove this part. So here is the proof. So let's start with the square of this sum. And we know this is yeah, so enough, so maybe okay, so this is how I should start. So enough to show that right, this is statement and that statement are equivalent, so we will just show this. So let's start with that expression. What is this? This we saw, this is equal to right, but since this is the case, why is that the case? This is the Cauchy-Schwarz inequality that we saw in the previous section. We have the real part of u dot v is also less than equal to this. Okay, this perhaps deserves a different color. All right. So we have that, and hence if we just use it here, what we get is right, and the right side is nothing but this, and we are done. This is what we wanted to show, that this is at most that this statement. Okay, so that proves the triangle inequality. So all of these facts are all familiar things from Euclidean geometry of the plane that we study in high school. It's just that the device of the inner product abstracts them out to any finite dimensional real or complex vector inner product spaces. Okay, so with that I want to end this lecture. Thank you for listening, and I'll see you next time.